Okay, so let me continue the discussion on principles of cryptography in today's class as well. If you recall, in the previous class, we looked at both about public key cryptography and symmetric key cryptography, how these can be used for ensuring the confidentiality of the data, how we can do the encryption and decryption using these two methods of cryptography. That's what we have seen. And in that context, we were looking at how one can use RSA in practice because it involves exponentiation, which is quite a time consuming process, especially when you want to send large size messages. It is damn slow. So in practice, what we do is we use both a symmetric key cryptography and also asymmetric key cryptography, where we use RSA kind of asymmetric algorithm to basically to share the keys, which are the like a session keys or the secret keys. Then we start using AES or other kind of symmetric key algorithm for encrypting the data because AES is much faster and there is no exponentiation as such involved in the case of AES or DS kind of algorithms. That way, in modern communication systems, we use both symmetric key cryptography and asymmetric cryptography to ensure the confidentiality of the data. So that's where I stopped the discussion. So before going forward, let me also give you a quick summary of how these two algorithms are different from each other. If you look at symmetric cryptography versus public key cryptography, as I was looking at earlier, in symmetric key case, we have a single secret key which is used both the encryption and decryption. If you look at the public key cryptography, we have two separate keys, one for encryption and one for decryption. And in the context of public key cryptography, we were looking at using the public key of the receiver to encrypt the data so that receiver who is having a private key can decrypt the message. Whereas in the case of symmetric cryptography, both have to agree upon having a common symmetric key using which they can encrypt and decrypt the data. So that is one key versus two separate keys. That way in this case, if the Bob also wants to send some data in a confidential manner to the Alice, then Bob also has to use another key pair of public and private keys. Whereas in the case of symmetric key, both Alice and Bob just require one secret key. Whereas in this case of asymmetric key, we need to have two pairs, one for Alice and one for Bob. I hope that distinction is clear. So if you extend this for in the context of n people who want to have communication over unsecure channel, where each of the end user require to have n-1 secret keys to talk with each of the n-1 people that he wants to talk with. And since I can use the same key in the both the directions, so it is effectively n into n-1 by 2. This is in the case of symmetric key. But in the case of public key cryptography, for each user we need to have one key pair, which is public and private key. And if you look at the user point of view, each user has to only keep one key, that is his or her private key, secretly. Whereas in the case of symmetric cryptography, each user has to maintain n-1 keys secretly. That way it puts a lot of burden or the tension on the users to protect their secret keys. That way asymmetric cryptography is much easier. And if you look at in terms of the kind of algorithms that are out there, we were looking at DES and triple DES. Nowadays what we are using is called AES. Then we also have something called RC1, 2, 3 and 4, where RC4 is one of the more secure cipher compared to the previous versions. RC4 also came from Ron Rivest, who also designed RSA symmetric cryptography. That means Rivest not only designed some symmetric cryptography algorithms, he also designed some asymmetric cryptography algorithms as well. And if you look at in terms of public key cryptography, we have seen RSA in the previous class, and I was mentioning that we also have something called Diffie-Hellman key exchange algorithm and also ECC, that is elliptic curve cryptography, which uses shorter keys unlike RSA. That way it can be quite faster and also secure. So these are the different kind of algorithms if you look at these two types of cryptographic systems. And if you look at in terms of symmetric cryptography, because it is quite faster for large data text, we will be using symmetric key cryptography, but we'll be using public key cryptography only for sending shorter messages. In other words, only for secretly exchanging the keys or such small amount of the data only will be using the public key cryptography, even though one can use it for actually sending the data that each user is interested to send or receive. And the last point is quite important. If you look at, we can use symmetric key cryptography for achieving confidentiality, authenticity, and integrity. Whereas if you look at the public key cryptography, which not only gives these three character properties or objectives, it also meets one other objective, that is non-repudiation. Basically, it means the sender of the message cannot deny at a later point that he or she has not transmitted such a message. That means using public key cryptography, we can tie the message, like very similar to the digital signatures, that this message is indeed sent by so and so. So one can prove that in court as well if needed. But that is not possible in the case of symmetric key cryptography. Today's class, what we look at is having looked at how we can use these crypto systems for confidentiality of the data. We'll look at how we can use these crypto systems also for achieving data integrity, authenticity, and also non-repudiation. So today's class will look at how we can build systems or the methods to achieve these objectives in the context of sending the data over internet or other kind of systems. That is the today's class topic. So any queries before I go forward? Anybody having any comments or any queries? Okay, if there are no queries, let me continue. Okay, so I'm going to talk about first on the integrity check of the data. How do you ensure that data that is received by other party is not tampered or modified in between? So that is the objective here, that we also call it as integrity check. So there are three broad schemes or the broad techniques that one can use for ensuring the data integrity in digital communication systems. First one is what you might have seen earlier, which is called checksum. The popular checksum scheme that you use is like a CRC16 or CRC32. I will talk about how one can use checksum and what are the disadvantages of using checksum for integrity check. Then we will talk about the message authentication codes, are also known as message integrity codes, how we can use this for integrity check and what are the problems with MAC codes. Finally, I will talk about digital signatures, how these are superior compared to checksum and using message authentication codes for ensuring that data integrity, authenticity, and also non-repudiation. So these are the three topics that we'll go through in today's class. Let's look at this TCP header. If you look at very carefully, we have 16-bit checksum field inside the TCP header, which TCP uses to check whether the TCP header, including its payload, is having any issues during the data transfer. In other words, whenever we have TCP communication happening between sender and receiver, the receiver of the TCP communication uses the integrity check field, that is the checksum, that here we use the CRC16, to check whether the message has been modified or tampered in between. And if you look at the reason why we use checksum field in the TCP header, this is basically to see whether the message has been modified accidentally, mostly because of some hardware issues or because of some noise or some accidental mistakes during the transmission of the data. So this checksum that we use it here, it is not really meant to guard the data against intentional attackers who try to tamper with the message. So your objective is very simply to see whether the message has been accidentally tampered because of underlying issues with the hardware or because of the some noise during the transmission of the data between the sender and receiver. So that is the purpose. The way TCP works is it takes the TCP header fields, it takes also the TCP payload, and also it includes the pseudo headers from the IP layer like IP source address, destination address, protocol number, and other fields to compute this CRC16 and include that 16-bit data along with the rest of the data while it is sending the packet to the receiver. So that at the receiver you check the checksum. That means you recalculate the checksum, and if it is matching with the checksum that is there in the TCP header, it means that very likely the message has not been tampered or modified because of some accident during the data transfer. So that is the major objective of using the checksum in the case of TCP header. And if you look at the layer 2, so if you come back from the transport layer to the data link layer, if you look at both Ethernet, that is 802.3, and Wi-Fi, that is 802.11 standards, they also have the FCS. We call it as a frame check sequence. We use here CRC32 algorithm for adding some redundant bits while you are sending the data to the other end of the link. So the receiver of the communication recalculate the CRC. If both of them are valid, both of them are matching, it means that message is free from any accidental bit errors because of the data transmission. So if you look at CRC16 or CRC32, these are basically kind of gives you assurance that the message is free from such errors as long as the bit errors length is less than or equal to 16 bits in the case of CRC16, and the bit error length is less than 32 bit in the case of CRC32. So we here use something called generator polynomial to compute the remainder by converting the entire thing into a polynomial and include that. So at the receiver side, we use a hardware level, the CRC algorithms to recheck this particular thing. Basically, you take the entire message at the MAC layer, and if the remainder of that particular generator polynomial, when you apply the message is 0, it basically means the message is free from any bit errors. Otherwise, there is some problem. And if you look at in the case of Wi-Fi, the TCP, not the TCP, in the case of Wi-Fi, the receiver of the Wi-Fi message doesn't give any acknowledgement whenever there is a failure of the CRC. The sender of the message, in the case of the unicast communication, has to retransmit the data, but if it is like a broadcast data, so it is gone and it is up to the higher layers to decide how to retransmit the data. And in the case of the Ethernet, also we have the CRC32, but here there is no acknowledgement from the MAC layer to the sender of the Ethernet packet. Again, in this case, it is up to the higher layers to decide how to retransmit the data. Most likely, in the case of TCP, we want the 100% reliable delivery of the data. In that case, the TCP sender retransmit. But at the link layer, we don't do anything to retransmit the data, even if though there are some bit errors that have occurred at the link layer. So that's what has been done in the case of Ethernet and Wi-Fi. And if you look at the reason why Wi-Fi has more stringent way of trying to retransmit the packet is because the probability of your transmission getting interfered or suffering from some bit errors is higher, because here we are talking about the wireless transmission. But in the case of Ethernet transmission, where we are talking about using Cat6 cable and where we are talking about the cable length less than or equal to 100 meters, the probability of your transmission suffering from such bit errors is very, very low compared to Wi-Fi. That's the reason why, yes, we use the CRC, but we don't do anything to correct the bit errors or ask the sender to retransmit at the layer 2. We leave it up to the higher layers like transport or the application layers. But Wi-Fi does something more stringently, where it tries to retransmit for certain number of times before giving up and letting the higher layers to deal with the retransmission errors. And if you finally come back to the IP layer, originally in IPv4, we have something called header checksum. Unlike the TCP checksum and the UDP checksum, which are calculated over the entire header and the payload, including the pseudo IP headers, the IP header is only meant for the header part of the IP packet. That's why the name, the header checksum here. It is also of 16-bit. And yeah, again, yeah, there are a certain number of fields that you can see it. But interestingly, if you go to the IPv6, the header checksum has been completely removed with the there are multiple reasons. One reason why it has been removed is, as I was mentioning, IPv6 assumes that pushes that responsibility of reliable data transfer to either the data link layer or also to the transport layer or the application layer. That is one reason. Other reason which is very important in the case of IPv6 is, if you have the header checksum, each router which receives the message has to recompute the checksum at each and every hop during the transmission. The reason why we have to recompute the checksum is the time to leave field, which is also called hop limit in the case of IPv6, is decremented by the router at each and every hop. Because there is a change in one of the fields in the IPv4 header, the router has to recalculate the checksum. And unlike in the case of IPv4, we remove this particular checksum in IPv6 because nowadays the routers involved in routing of millions of packets per second. When you're talking about such a huge packet processing or packet forwarding at the router level, asking it to recalculate the checksum drains away a lot of resources from the router side. To address that, what has been done is let either the higher layers or the lower layers take care of the reliable data transfer or the integrity check of the message by removing the checksum or the header checksum from IPv6 header. So in summary, what I was trying to say here is, in all modern communication systems, here I'm talking about Ethernet, Wi-Fi, internet in general, but if you also look at even in the cellular also, we use, for example, in 4G, we use a CRC24 at the physical layer. We don't use it at the MAC layer. We use the CRC24 at the physical layer in 4G LTE standard. But all these are basically meant to guard transmission against accidental bit errors. This could be because of occasional errors that are induced because of some hardware faults. The probability of that is very, very low. It is very minute possibility, but still there is some chance that that could happen. Or it could be because of the interference or noise that is possible in the case of wireless transmissions. But all these checksums and CRC things that I was talking about, these are not meant to guard against the message, especially when the attacker is intelligently want to modify the message. If you come back and look at this particular message here, but we can take any message. If you look at this message where you are calculating the CRC, if there is a man in the middle or some attacker who is eavesdropping to the communication between the sender and receiver, what the attacker can do is, attacker can receive this particular message, the entire message, and rather than transmitting this message as it is, the attacker can construct or modify this message. And because the CRC algorithm is also well known, it is like the crypto algorithm that I was talking about, including the what kind of generator polynomial that you use for calculating the remainder, everything is known. So that way attacker can modify the content of the message and insert modified CRC. By doing that, whenever the receiver receives this message, receivers also can recalculate the CRC, but everything looks perfect for the receiver because it doesn't see that somebody has tampered with the message. That way, the plain checksum only guarantee you the data integrity. but it doesn't guarantee the authenticity of the message. It doesn't say whether the message is indeed transmitted by so and so. That particular guarantee and including the non-repudiation guarantees, these guarantees are not achieved by checksum. And because of these reasons, we say the checksum that fields that you have seen so far are called kind of having poor cryptographic characteristics. And if you look at the example that you see at the bottom of this illustration, we can take a message of certain length, and if we convert that message into ASCII characters in a typical checksum, if you look at the uh, if you look at the word and the origin of this particular word, we are basically taking a sum of the various characters that are part of the message. You take the message, you convert it into the ASCII, and we are simply doing the addition or basically the sum of the message, and you are including that. And at the receiver again you recalculate the sum and verify whether both are matching or not. So this is in the case of a naive checksum based approach for checking the integrity of the message. As you can see in the illustration, by flipping these two, for example at the sender side we have 1 here and 9 here. By flipping these two digits, we still end up getting the same checksum if you start using the simple checksum based approach for data integrity or the message integrity. To address this, what has been done is the usage of the CRC techniques like CRC 16 or 32 or 24, which basically guard against more number of bit errors, and these kind of occasional things can be protected, but still it is possible for some man in the middle attacker to modify the message and reconstruct the CRC as per the well-known CRC algorithm, and everything looks normal when the receiver try to check the message. That way we can get the data integrity but not authenticity of the message by using the checksums. That's the reason why we use the word. These checksums are having poor properties with respect to the cryptography. So any comments before I start talking about other two techniques for data integrity? So any comments from anybody on usage of the checksum for data integrity? No comments? Okay, since nobody is asking, let me ask one query. So do you know why the CRC is at the flag end of the message? Do you know why? Especially at the data link layer, we keep the CRC not at the beginning of the message, we keep the CRC after the payload. If you look at very carefully, this is a payload coming from LLC layer and the IP layer. Then to that we are adding the CRC. Do you know the reason why we have CRC coming at the end of the message, not at the beginning of the message? Anybody?
Like if it's already in the order, as the packet comes, it can keep adding the bytes, right?
Yeah, Arsha, you're kind of right. Basically, what happens is, as I was mentioning, the CRC calculation happens at the hardware level. Whether it is like if it is like Ethernet or it is like a Wi-Fi NIC, the network interface cards, as soon as it is going to receive the message with these particular fields that you can see it here, the receiver hardware start keep calculating the CRC as it keeps coming. So by the time the CRC field comes at the receiver, it can immediately verify and see whether it is matching it or not. But if you put it at the beginning, it is of no use. That's the reason why we keep it at the end, and on the fly you start calculating it, and there won't be any delay by the time you receive the rest of the payload. Okay.
Sir, why does Ethernet require interframe gap but not Wi-Fi?
No. Again, so I couldn't get. So even in the Wi-Fi also we have this interframe gap. When I say interframe gap, it basically means the delay between transmission of two messages over the shared medium. It could be like Wi-Fi or it could be like Ethernet. So this gap is there, but this illustration is not showing.
Oh, okay.
Both of them having it.
Thank you.
Okay, let's look at the second one for data integrity or the message integrity, that is called message authentication code. It is also known as message integrity code, like MAC or MIC. Don't confuse MAC with the MAC, that is the medium access control or the MAC address that you very popularly use it. So here we are talking about the message authentication code. This is how it works out. When you take Alice and Bob, Alice wanted to send a message. So there are many standard MAC algorithms that are out there. Again, these are algorithms are also public, similar to the way we have seen encryption algorithms. Only that is not public is the key. So you take the message that you wanted to do the integrity check. To that you supply one secret key that is known only between sender and receiver. So what this MAC algorithm does is it generates a fixed length digest or hash of the message, that is called MAC or MIC. So the sender basically sent the message along with the MAC. Here, if you look at very carefully, we are not converting the message from plain text to the ciphertext. Message is going in the plain text as usual, but along with the message, we are also sending some tag. In this case, the tag that we are sending is the MAC, the message authentication code, which is a kind of a hash that is generated by using the message and the secret key that is known between the sender and receiver alone. So because of that, the MAC is also called as keyed hashing. What we are doing is something called hashing, but for doing hashing, we are also applying some key. So all of you know about the hash algorithms, which basically generate a fixed length hash when you use certain input to the hash algorithm. But what we are doing is, rather than simply giving some input, we are also giving some key, like a salt kind of thing, so that we can get something of fixed length, which you append along with the message while you are sending the receiver. At the receiver, because the receiver is also having the same secret key, and also the MAC algorithm is also well known to the receiver as well. It recalculates the MAC. Both the MACs are matching. It basically tells two things to the receiver. When the MAC is matching, the receiver comes to know two things. One is the message is not tampered or modified in between. That is one thing. And also it kind of proves to the receiver that the message has indeed sent by the sender. So the message authentication code gives you two things which was not possible with the checksum. One is the data integrity and also the authenticity of the message. I hope this part is clear to all of you. So how it is possible to get two things, to achieve two things with message authentication codes. One is the data integrity and other one is authenticity of the message. So can somebody say how it is possible to have authenticity using the message authentication code?
Like somebody, the man in the middle, he doesn't know the key, so he can't generate MAC
Yes.
according.
So by here the assumption is only the sender and receiver have the secret key. And if there is a man in the middle, yes, man in the middle can get the message, the message that sender is transmitting, but it is not possible for the man in the middle Yes, man in the middle can modify the message the way he or she wants to modify, but it is not possible to generate the MAC with a key that is only known with the sender and the receiver. So by assuming that the secret key is not compromised, which is not available to the man in the middle, the successful verification of the MAC at the receiver also guarantees that message has been indeed transmitted by the sender or the whoever is having the whoever is having the secret key. So that way we assume that sender and receiver have to, they keep the messages, the secret keys secretly and use this MAC to ensure that the message is integrity protected and also to guarantee the authenticity of the message. So that way we will get two things using the message authentication codes. But one thing that is not possible with message authentication code is the non-repudiation. That means non-denial of the source of the message. In other words, let me explain. If you look at this particular case, let's look at this is Alice and this is Bob. Alice has sent some secret message, some message. I am not saying it is secret because as you see the message is going in the plain text. And Alice has also sent the message authentication code which Bob has received. And Bob has verified the authenticity of the message and Bob comes to know that it is indeed coming from Alice. So that part is clear. But there is nothing that is stopping Bob to modify the message that he received and generate a new MAC and send this message and the new MAC to somebody stating that this is the message that I received from Alice. You got my point, right? Let's say Alice has sent some message to the Bob. Now what Bob could actually do is, because the Bob already has the secret key with him, he can modify the message received from Alice and generate new MAC and send the combination of the modified or the tampered message and the modified MAC to the third party, whoever he wants to say that so and so was sent to me by the Alice. So because of that, it is not possible to stop the Bob doing this kind of non-repudiation kind of thing. Does that make sense what I said to all of you?
Yes,
Hello, and also take one more scenario. I was talking now with respect to Bob. I can also say same thing with respect to Alice as well. Let's assume that Alice has sent the message to Bob, and Bob wanted to submit this to the court, stating that so and so was sent to me by Alice. But Alice can actually deny that she has indeed sent this message because Alice here can claim that no, this is not what I have sent to Bob. What I have sent to Bob is this one, and this is the message authentication of message that I sent, which is quite different from what Bob is trying to show to the court that so and so was sent by Alice to me. So why all this confusion is happening here is because, can somebody say why we don't able to offer here non-repudiation guarantee here? Why that is happening here?
So because the key is shared.
Exactly. So either Alice can start cheating Bob, or even Bob can start cheating Alice, or kind of saying that it is indeed sent by so and so, even though so and so has not sent that message. Yes, you are right, because the key is shared between Alice and Bob. Because they are using the same key, I can regenerate a new MAC on the tampered or the modified message. So because of that, the message authentication codes, which are based on symmetric key cryptography, don't give the non-repudiation guarantees, which are also equally important when you're talking about secure communication over internet and other media.
Sir, I think
Could you
we can
explain in the
solve this problem by using a third party that is trustable.
Tell me again, Shubham.
Sir, I think here we can have a trustable third party that will keep track of the keys, sir.
No. Here, if you look at the key, here Bob and Alice are using a common or a shared secret key. But how using a trusted third party will help them?
Sir, I think it can keep the record of sessions and the session keys. And
Uh, so, no, which is the session key? See, here I'm talking about a single key here. I'm not talking about, let's say that you want to send one document, and along with the document, you are adding the message authentication code. So I'm not talking about the secure communication here. Here I'm talking about the data integrity alone. Uh, Madhuri, you are right. I'm coming next to the digital signatures, which kind of also addresses this last issue with the message authentication codes. That is, how do you guarantee the non-repudiation? Digital signatures don't suffer from this issue, because if you look at digital signatures, there the key that you used for signing the message is only known to one party, so that other party, so that other party can tie them to that particular source, even if he or she start denying that they have sent so and so message. I'll come back and talk about the digital signatures in the following slides. But I hope it is clear. The main problem that is happening here is Alice and Bob are using common key, and that makes one of them start denying that they have indeed sent the message, because they can reconstruct a new MAC for the modified or the tampered message. And if you're talking about the man in the middle requires to have this particular secret key. So far, we are not assuming the man in the middle is having the secret key. We ignore that. With respect to Alice and Bob itself, you have the problem here. Either Alice can start denying that she has sent the message, or even the Bob can also start saying that this is a message sent by Alice, even though she has never sent the message. So because of the sharing the secret keys, which are based on the symmetric cryptography, we have the problem with the message authentication codes.
Sir, here if the symmetric key is shared using a public and private key system, then can't we say ensure non-repudiation?
So
Using the public and private keys, key sharing algorithms, if this key is shared between Alice and Bob, then
yeah, Ranjita, if you look at, we are using the public key cryptography to secretly share the key between Alice and Bob. But if you start understanding the problem of non-repudiation, Alice itself, she is saying that she has not sent the message, even though she has sent the message. So here the problem is not about how to share the key. So we can use the public key cryptography, or we can use the Diffie-Hellman key exchange algorithm to secretly share the between Alice and Bob. But here the question is, Alice is denying that she has sent the message to Bob, or Bob is trying to claim that he has received a message which Alice is saying that she never sent in the first place. Non-repudiation means denying that you have sent so and so message.
Yeah, sir. That I understood. If Alice is denying that she have not sent the message, and then Bob has the message, uh, which he could cross-check the MAC using the secret key, which was shared using the public key crypto system. Then public key crypto system makes sure non-repudiation, right?
Public key crypto system says non-repudiation of the symmetric key. That's what you mean?
Yeah, I mean, if a key was shared using a public key crypto system, can the sender and receiver deny it?
No, no, they can deny because no. See, if you look at the problem, Ranjita,
I think maybe I'm confusing.
the problem is Bob can always construct any message. If you look at here, the Bob here can construct any message and apply the MAC using the key that he has shared with Alice and submit that to the court stating that this is a message that I received from Alice, even though Alice was never sent such a message in the first place. So, is there any way to stop Bob doing that particular thing?
Okay, sir, got it.
Got the point?
Thank you. Yeah, thank you.
The problem is both of them are using the same key. That is the thing that is the problem here. Somebody is saying that is the mix same as Mac. I was saying the same thing if you recall. Message authentication code is same as message integrity code. Yeah. Okay, so let me continue if there are no other queries.
Sir, 1 minute, sir.
Yeah.
Sir, here you said that if even if Alice did not send the message to Bob, and Bob has constructed his own message and has shown that this message was sent by Alice. That's what non-repudiation is, right?
Yes, right. Yes,
But
right.
the thing is, the thing is, when there is no kind of communication, and when Alice didn't want to send any message to Bob or something like that, why will this key be shared, sir?
No. Again, see, there could be, you can take a scenario like Alice and Bob are exchanging 10 messages. Out of that, 9 messages are the one both of them agree upon. But there could be one of the message where all the critical or maybe the financial data is there. Like maybe they want to say that you have to send me so and so message, and using so and so method on so and so date. Let's say the entire thing is divided into several messages. Out of that, one of the message where Bob can say that can modify and say that this is what you sent to me, even though she has sent something else or she has not even sent that thing in the first place.
Yes, sir. For example, if 9 messages are on agreement of sender and receiver, there are nine packets to be sent, and the receiver has created its own 10th message. Then we can easily find it out that after for the last segment, what we get, the last packet, what we get any more fragments as 0 in one of the header field, no, sir. So then the 10th message will be invalid only.
Okay, so what you are saying is that once they agree up, okay, what if I would say that they have agreed upon to exchange 9 messages, out of that 8 messages, they both of them don't have any denial or any issue, but one of the message has been modified by Bob in a manner that Alicia is saying that she never sent such message. What do you do in that case?
Alice has to send the 9th message as well, no, sir?
No, that's what I meant. Let's assume that they have let's make it simpler. There are 2 messages both Alice and Bob are exchanging.
Yes, sir.
Both of them agreed that they have exchanged 2 messages. But on one of the message, Alice is saying that this is not what I have sent to Bob. But Bob is saying that no, you only sent this message to me.
How then here MAC will be compared, no sir? If both the
Yes,
both
you
the
are right.
MACs are
You are exactly right. The message sent by Alice will have some MAC, and the modified message, assuming that Alice is the one that is trying to cheat here, the message that is constructed by Bob will have another MAC. I agree that this MAC and that MAC are different, and both of them, let's end up going to the code. And Alice is saying that this is the message that I sent with this particular MAC, and Bob is saying that no, this is the message sent by Alice, and this is the MAC. Who is right and who is wrong? Nobody can prove that who is trying to cheat here, because both of them have the same secret code.
okay.
So that is the problem here. Here the data integrity is there and authenticity of the message is there, but what is not there is we cannot give the non-repudiation guarantees.
Oh, you are just saying that this key value is shared only between these two, and we can't really say who is right and who is wrong.
Exactly, because anybody can try to construct any message of their kind and say that
Yes.
this is the message my friend has given to me, even though this is what I myself constructed, and trying to say that this is given by my friend.
Okay.
Right?
Okay. Yes, sir.
So, any other queries? Anurag, are you trying to say something?
No query, sir. Just an observation.
Okay. So, what is your observation?
Sir, similar to how we said AES needs to encrypt different blocks with different key. Here, if Alice and Bob are using same key for a long time, and once the attacker captures all the messages, suppose Alex sent "I love you" once, he captured it along with Mac, and "I hate you" along with Mac. The next time, if Alex sends "I love you," Bob, the attacker can just change it to "I hate you" because he also has the Mac, right, which was sent earlier.
So, basically, you are trying kind of saying the replay kind of attack.
Replay.
Yeah. That is also possible. And also, I will talk about this further in the following slides. So, here, compared to the size of the message that you wanted to integrity protect, the MAC that you generate is of very small in nature, like 48-bit or 128-bit. It is more like a hash. So that way, there could be many different messages. They could be mapped to the same MAC. Okay, that is the case. There is a possibility of a replay attack, and also I will talk about in the following slides. There is also possibility of known plain text attack that is possible. I will come back and discuss that. Okay, so before I talk about digital signatures in detail, so this is the beautiful property of RSA or the public key cryptographic systems that makes them also used as digital signatures. That means if you have any plain text message, whether you encrypt using the public key and then try to decrypt using private key, or you try to encrypt using the private key and then try to decrypt using the public key, the output is exactly the same. That means when I was talking about the generation of the key pair n comma e as the public key, n comma d as the private key, you can also make n comma e as the private key and you can make n comma d as the public key. Only thing is there are two keys. One of them you can designate as private key and other one is you can designate as the public key. And this beautiful property holds. Because of that, we also use RSA also for digital signatures. Here the idea is, as I was mentioning, for data integrity and also guaranteeing authenticity of the message along with the non-repudiation guarantees. So let's look at this example. The example is showing Bob wants to send some secret message or like a love letter to Alice, where he has composed some love letter here that we are calling it as message M, which is subjecting to the public key crypto algorithm using his own private key. Then what you send over the network or over an insecure channel is the plain text message M and also the encrypted message, where the message is encrypted using the Bob's private key. When the message is received by Alice, Alice anyway can read the message, but she wants to make sure that message was indeed sent by Bob and it was not tampered. For that, what Alice has to do is, Alice, knowing the public key of the Bob, will apply public key of the Bob on this encrypted message or the digitally signed message. We call it here, we don't call it here encrypted, we call it as digitally signed message. Then get back the plain text message. By comparing these two messages, Alice can verify whether the message has been tampered or not. Very similar to the message authentication codes, the digital signatures also provide you both the integrity of the data and also ensure the integrity, and also they guarantee you the authenticity of the message. Here, only the Bob only knows his private key, and if I am able to decrypt using the Bob public key, and if it is matching with the message M, it means that the message has been indeed sent by Bob, not by somebody else. So that way it also guarantees the authenticity of the message. And yeah, so I think that's what I was talking about. And also it gives you the non-repudiation guarantees. Here in this case, Alice can take the message M and the signature, that means the signed message, that is the message that is sent by Bob, by encrypting the message using his private key to the code and prove that Bob has signed. So this is exactly what I meant by non-repudiation. Alice can take Bob to the court. That means Bob cannot deny that at a later point that he never sent such a message. That is because Bob only has his private key, and everybody, including the lawyers, know what is the public key of the Bob. By applying the public key of the Bob on this signed message, everybody can find out what is the plain text, and they can check that one with the plain text that is there. If both of them are matching, means it is indeed sent by Bob, because Bob only knows or has his own private key, nobody else. But there is a bigger question that arises, that is, what if the private key of the Bob is compromised? Again, so that is actually the problem with the Bob alone. It is his responsibility to keep his private key secretly. If his private key is compromised, again, he is held responsible because he is not the one who is able to properly maintain his private key, but still he is responsible, and Alice is not responsible, or Alice can bring him to the court and say that, yeah, this is the message that I indeed received from Bob, or somebody who has known the Bob's private key, for which also Bob is responsible and has to honor the agreement or whatever that we are talking about. So that way we can get all the three properties. One is the data integrity, other one is authenticity of the message, and also non-repudiation guarantees when you use the digital signatures. So any comments or any queries from anybody? But still there is a problem with the way I have described about using the digital signatures. That is, if you go back and look at this slide here, look at here. In this case, we are applying, or basically here, the Bob is signing his message using his private key. He is signing the entire message. So what is the meaning of signing the message? Assume that message is M. So what exactly mean by now signing the message in terms of the RSA algorithm? In RSA, what the signing of the message with the Bob's private key means? So if we assume that M is the plain text, that Bob wants to transmit. Now in this case, what Bob is doing is using his private key. So this is the what I mean by signing of the message here. So this message could be of arbitrary length. Let's say you want to send a PDF file of 5 MB. So we are talking about this large size message, and here we are talking about D, which is typically of order of 1024 or 2048 bits. So now we are talking about of course we don't do M as it is. What you do is you decompose the message into smaller chunks. For each of the smaller chunks you do this exponentiation with D, which is of size 1024 or 2048 bits. So that basically we are talking about exponentiation with, if you're talking about 2048, now we're talking about very, very large, like 617 digits it will translate it. We're talking about exponentiation with really very huge number. So as you can expect, it is really time consuming. So because of this, we don't really use public key cryptography to sign the large messages. Also, we don't use the public key cryptography to encrypt the large messages. I discussed about the second point earlier. Now I'm talking about why we should not use public key cryptography for signing the large messages. So we should be using it to sign only the small messages. We call them as message digests. Okay. So because it is quite expensive computationally to encrypt the long messages in public key cryptography algorithms, what we do is we use the hashing, like all of you know about the hash algorithm or the hashing techniques in general. So where these hash functions take the large size messages of arbitrary length, but they beautifully generate a fixed length messages. Like this message could be like 64 bit or 48 bit or 128 bit, whatever it is. No matter what is the size of the input, the hash or the digest that you generate here is of fixed length. So we use the notation h comma m to designate the hash that is generated on m. And now what we are talking about is secure hash algorithms or the secure hash functions. These are quite different from what you might have studied in data structures and algorithms course, where also you might have studied about the hashing as a data structure, where you use a fixed length array, which basically takes records of arbitrary length, and you index into the hash table, and if there are any collisions, you start doing the chaining whenever there is a collision and all that. So but you might have not spent a lot of time looking at how different hash algorithms work and how to reduce the collisions when you are doing hashing and other things. But what we are going to talk about here is about the secure hash functions. When I'm using the word secure not in the context of giving the security or the confidentiality for the messages that you transmit. The security is in a different sense here. Let's see what I mean by security in the following points. First one is these hash functions are like one-way functions. There are no keys involved here. So that way these are quite remarkable compared to the encryption algorithms, which are like a two-way functions with the involvement of the key. That means there's a use a key to encrypt the message and use either the same key or a different key to decrypt the message. That is in the case of encryption. Whereas in the case of hashing, there is no key involved as such, only there is a hash algorithm that is out there. You submit a large message to the hash algorithm without involving any keys. It is generating a fixed length digest of the message. And as I was mentioning, could be a chance that multiple large messages could end up providing the same digest. Whenever that is happening, we say that there is a collision. But we say that a hash algorithm is secure only when such collisions are practically impossible. Okay. In other words, if you are given a message digest X, that means if you are given this particular thing, it should be computationally impractical to find a pre-image. When I say pre-image, M dash, such that h equal to x equal to h of the m. That means if somebody gives you a digest, you cannot figure it out with the computational resources that are at our disposal, even with the supercomputers. What could be the m that has generated such h of m? Similarly, it is also practically or computationally infeasible to find two messages m and m dash in such a manner that h of m equal to h of m dash. Okay, so only those hash functions which have these properties like non-reversibility, that means going back to m if you are given h of m, finding m dash when you are given m which is having the same hash like m, if they are computationally impractical, we call such hash algorithm as the secure hash algorithms. One such hash algorithm that all of you might have heard about is MD5, which was supposed to be a secure hash algorithm or the cryptographic hash algorithm, which generates 124-bit message digest. Okay, but of late in 2005, it was found to suffer from collision attacks, and people have come up with the solutions where in less than few seconds you can find multiple messages which can translate into having the same hashed value. With the ordinary computer like Pentium PC, you can be able to do that. So that way it is no longer secure hash algorithm, but one can still use it to transmit ISO images and all. You might have seen many times when you are downloading any images or any installation images on internet, you also see them providing you the MD5 digest as well. That is basically to see that whether your executable file has been corrupted during the transmission from that particular web server from which you are trying to download the image. So to guard against such kind of accidental errors, one can still use MD5, but we cannot use MD5 for the secure hashing algorithm because it is no longer having such a strong collision resistance. So to address that, NIST has come up with secure hash algorithm, like SHA here stands for secure hash algorithm. Again, there is a SHA1. 2017, Google and many other companies have found that these are also having lots of vulnerabilities. Of late, what we started using is the SHA2, which can generate a digest of length all the way up from 224 bits to 512 bits. And even when you are talking about hashing the passwords, one should be using the SHA2. And even in the case of digital signatures, I'll talk about how we'll be using the digital signatures and password hashing in the following class. But one can use this thing, and even SHA3, which can generate digest of arbitrary length, which is also has been standardized by NIST. As soon as somebody has found vulnerabilities with SHA2, maybe the rollout of the SHA3 will happen. And also there are lots of other issues with the usage of the SHA3 because of that rollout, because sometimes doing all these things involves modification at the hardware level, because all of them are computationally quite intensive. You don't want to do these things at the software level because the current computers don't have the proper hardware mechanisms for taking care of this. The rollout many times will be delayed. But as of now, all of us use SHA2 when you're talking about password hashing, or when you download any digital signature, whenever you are trying to verify authenticity of the messages, you will be using the SHA2. Again, SHA2, use the word SHA224, SHA256, SHA512. Basically, it means the length of the digest that is generated here. irrespective of the size of the input message size. These are designed by NSA, that is National Security Agency in the United States of America, but have been standardized by NIST. So this is how one can use message digest in the context of the digital signatures without requiring you to spend too much computational overhead in generating the digest using the RSA keys as it is. Look at what is happening at the Bob site. Bob is having a large message. So what Bob does is using the, let's say, SHA-2, he generates a message digest, that is H of n. Let's assume that he is using digest length of 512 bits. Then H of m is of 512 bits. Then what Bob does is he takes his private key along with this hashed value and encrypt using the public key cryptographic algorithm. And here we are not talking about a large size message. It is of size 512 bits or 256 bit. So that way it is not that much computationally intensive to generate the encrypted version of the digest. So what we got from the message is the digest. After encrypting with the Bob's private key, what we got is the encrypted version of the digest. So finally, when Bob is sending over an unsecure channel, what he is doing is he is sending the message in plain text, plus Bob is also sending the encrypted version of the digest together. Okay. And look at what Alice is doing here. She receives both of them, both the message and the encrypted digest. And on the plain text message that she received, by knowing the hash algorithm, she generated the H of m. Since Alice knows what is the public key of the Bob, she can decrypt the encrypted message digest to get back the H of m. If both of them are matching, it means that a message has not been compromised and a message has indeed encrypted using the Bob's private key. This also ensures that Bob cannot deny that he has sent that love letter to Alice at a later point, so that Alice can take it to the court or to her parents or whatever is the case. So any queries or any issues or any comments on this slide? So this kind of summarizes how we can use public cryptographic schemes along with secure hash functions to able to generate the digital signatures, which helps in you guaranteeing the data integrity, authenticity, and non-repudiation guarantees.
Sure. How can one say that this particular public-private key pair belongs to Bob?
Yeah. So that is the topic of our next class. So we use something called public key infrastructure, which is comprises of various certificate authorities. Like you might have heard about VeriSign, DG certificate, and even the Google, and there are lots of such certificate authorities that are out there who basically do only one thing. They tie one public key to one entity on internet. As you are saying, Anurag, this trusted third party, which we call it as a certificate authority, can tell you that so and so is indeed the public key of the Bob or Alice or whatever it is. So job of the certificate authorities is to tell you that yes, this is indeed the public key of so and so. So that way we are trusting on somebody else so that Alice can trust Bob and vice versa. But also there are lots of interesting attacks on these trusted third parties as well, and there are also very interesting court cases on these certificate authorities as well. So I'll discuss that in the following class. But for timing, assume that magically everybody who are want to do the secure communication knows the public keys of other parties without any question on whether the public key is correct or not. For timing, assume that such thing is possible.
Hello, sir.
Yeah, go
So,
ahead.
yeah, in this case, we were sending large message and encrypted message digest. So, this message is exposed to public, like we are not applying any encryption algorithm here. So it can be compromised, like it can be accessed in uh, public.
Yeah, it can be compromised, but let's assume that this message is compromised.
Mm-hmm.
But let's assume that Bob has sent this love letter to Alice. Let's
Okay.
assume that Trudy has seen this message in between. She is converting this love letter into a hate letter.
Mm-hmm.
But can you tell whether Trudy is successful in Alice believing that Bob has sent a hate letter?
No,
No, exactly. So that's
no,
why.
because the message digest is cross-checking at the time of the receiving. But my query is the message is exposed, right? Someone
Yes, yes.
can read
In
it.
other words, the digital signatures are not meant for you to send
Mm-hmm.
confidential information.
Okay.
See, right? Many times, these are analogous to our signature that you do it on plain paper. Signature
Mm-hmm.
basically says so and so, like you get transcripts from, let's say, IIT Hyderabad, which is signed by our dean academic and the directors. So there is no confidential information out there, right? You can your transcripts. Whoever wanted to verify your transcript, they want to see what grades that you have received and whether the signature on this transcript is genuine or not.
Okay. Okay.
So there is no confidentiality here. For confidentiality, I'm not talking about the confidentiality. If you really want confidentiality, what you do is the entire thing, whatever I said, you put again using the secret key. That means take this message, comma, the message digest, and encrypt using the secret key that is known between Alice and Bob.
Okay. Okay.
So that way you have both then you have the confidentiality, authenticity, integrity, and non-repudiation. You'll get everything in one shot.
Okay. Yes, got it.
Got it.
So, yeah, so every time we are sending, along with the message, we are sending the message digest. So, means it seems like a overhead kind of thing for me.
So
So,
what do you want to send? What do you want to send? You don't want to send the message?
no, actually want to send the message, but not in that manner that we are, along with the message, we are sending, means a lot of data, means
No, data is
over.
not a lot of data. I think Rahul, I think I
Mm-hmm.
forgot to complete that description. If you go back here, so this is a lot of data. Look at here what we are doing here. Bob has message M.
Mm-hmm.
What Bob is doing here is signing the entire message. So look at here. Here, Bob is sending two things. Let's assume that message is of size 5 MB. So here Bob is sending the message of length 5 MB. Bob is also sending signed message of size 5 MB or more, depending on what is the size of the signing. In a simplistic case, you can assume that the message size that you are trying to send here or the signing, after signing, it has kind of become doubled. Because
Correct.
here the Bob is signing the same message. He is not signing here the digest of the message. When I was talking about the secure hash algorithms, what Bob is doing is he is taking the message and generating either 256-bit or 512-bit digest, and along with the message he is only sending a small tag. So that way we can kind of reduce the overhead, and at the same time another beautiful property that you can get by signing the digest and not signing the message as usual is you can guard against known ciphertext attacks. So if you recall our discussion on known ciphertext attacks, So what is the meaning of known ciphertext attack? The attacker or the man in the middle knows pair of the plain text and the ciphertext. That means M1 comma C1, M2 comma C2. If the attacker gains access to many such pairs of plain text and ciphertext, it becomes more and more easy to do the frequency analysis and other techniques to able to understand what is happening between Alice and Bob. That is the case of known plain text attacks. In this case, if I start sending the signed messages of the plain text as it is, that means M comma C, the attacker can launch the known plain text, known ciphertext attacks. You can stop the known ciphertext attacks by doing this. So by sending only the digest, this digest, there could be a large number of messages for which same digest is possible. As I was mentioning, practically it is impossible to do the reverse of, basically doing the inverse. Given h of m, finding m is impossible. That way attacker, even though attacker has both a message and, of course, anyway, see, everybody has Bob's public key. Even the attacker also can decrypt this message. You understand what I'm trying to say that? Let's assume that an attacker receives both the message and this encrypted message digest. Because attacker also knows the Bob's public key, this part is gone. Then the attacker has the message and the h of m. As I was mentioning, it is cryptographically impossible to find what is m that is corresponding to h of m. So it is not possible for the attacker to launch known ciphertext attacks only when they have m comma h of m. But if they have m comma c, if you have such many m comma c's, it becomes easy to crack. It is kind of known plain text attack, known ciphertext attack.
Yes.
Okay, so last
Okay.
slide for that. Yeah.
So message digest is just a small kind of a small message thing.
Yeah, I was mentioning, right? It is typically of length 224 bits,
Okay.
not bytes even. I'm talking about bits here. Okay, remember here it is either 224 or 256 or 512 bits. But the message that you typically send could be of any size. Let's say you want to send a video file to your friend, and it could be, let's say, 1 GB. But for the entire 1 GB of the video file, you are only adding a small tag of 512 bits.
Okay.
So that the receiver can verify that this message has not been tampered in between and this has indeed sent by you, and later you can never deny that you have sent such a video file to your friend or to other party, whoever you are trying to communicate. So it gives you all the guarantees. But if you want to secretly send the message, you take the large message and the encrypted message digest, encrypt that using a secret key that is known between you and the receiving party, so that you achieve the confidentiality, integrity, authenticity, and non-repetition guarantees.
Okay. And one solution I was thinking about is if we are sending a message and first we means a message is A is sending to B. So first if we encrypt the message using the private key of A and the again encrypting it using the public key of B. So if we send this message at receiver, if we decrypt using the private key of B and then public key of A, so that can also be achieve a kind of authentication because we are first we are decrypting this message using the private key of B and again it using the public key of A. So double encryption kind of thing I was thinking.
Yeah, you can do all. See, again, you can do any number of encryptions, decryptions, and all that. Yeah, all these are possible. Yes, you can do that. But at the end of the day, everybody has to agree upon some standard way of encrypting and decrypting. And what has been agreed upon in the internet communication is what I'm showing it here.
Okay, okay.
Yes, but you can do it in multiple ways.
Yeah, got it.
And also you can also come up with your own. See, the way you are describing, if you don't want to follow the standard convention of the way you encrypt and decrypt and ensure the integrity of the data, you can do, but as long as you and the receiving party agree upon what should be the process to be followed for secure communication.
Yeah.
Okay, Rahul?
Yes, yes, yes.
So any other queries from anybody? I think we are already reaching 4 o'clock. Any other queries? Okay, so if there are no queries, so all of you have to remember that cryptography is not one solution with its magic wand can address all your security problems. And if you look at one of the famous quote from Shamir, he says that crypto will not be broken, it will be bypassed. So, I think if you remember the video lecture, I mean the Google talk given by David Clark, he also talks about that the people who thinks that they have to break the crypto system to compromise the communication. So they are like crazy people. So there are many ways of breaking the secure systems without you bothering about spending millions of years cracking these secret codes. One such thing is shown in this particular cartoon. So that is the problem. How do you make people securely maintain their keys? And if you have read the news of late, there is somebody who actually lost their passwords, and because of which they, I think around $220 million of bitcoins are actually lost. Basically what they have done is there is a private key, and in the bitcoins also people use both public and private keys, and you have your private key, but you don't want to keep your private key as usual, right? Let's assume that you have a public key and private key, but you don't want to show your private key in plain text, because if tomorrow if some malware or Trojan horse installed in your computer, so they can steal your private key and start impersonating you. So many times what people do is they also password protect the private keys. Unfortunately, this man, because he received this particular thing as a gift many years ago when the bitcoins were not so popular, now it is so many millions of worth, and he forgot the password, and I think he has only 2 attempts left. And if he is unable to guess with the remaining 2 attempts, so forever you lose the bitcoins, because there is no way you can recover. So that way private keys are good, they give you a lot of benefits, but if you forget it, the way you talk with credit card companies and banks and even the Google, like the way you approach our computer center whenever you forget the password, here you are the sole party who knows what is a private key. There is nobody in the world knows what is your private key or what is the password that you set. If you lose, it is the end of the story. Okay, also, I think, yeah, this is also important point. Yeah, I think as Rahul you are mentioning, the cryptography systems only give you the, if you look at the CIA Trinity or the triad, where the confidentiality, integrity, and availability. So using cryptography, we can only address the first two parts. If you look at the internet architecture, so cryptography has been used to address both the confidentiality issues and the data integrity issues. But availability is still a big issue, and crypto cannot do anything to you to guarantee the availability of the messages and other things in internet communication. So that way, crypto is not end for all your security and for not the network security for that matter. Okay, guys, any queries, any last queries from anybody? I can spend 5 minutes. Otherwise, if you have other classes, please carry on. Okay. Anybody having any other queries?
Sir,
Sir,
ultimately these. Okay, sorry.
Yeah, Prashant, yeah.
Yes, sir. Please share this video recording on the classroom because there was some network issue in between.
I think I am posting all the videos, right? If you are,
Yes, yes, correct, correct.
I will see. Typically, at the end of the day, I post all the reading material and the slides and the video lectures, everything. Okay.
Yeah, thank you, sir.
And also, I will try to post some queries so that you can able to answer to better judge how well you understood the concept that I taught. Okay. I will do that.
Okay, sir. Okay.
Sir, Anthony sir had said wires arc and socket tutorial, but when we click now, it says that it is not available.
You mean the video lectures? You mean or the?
The video lectures were there for socket and wires arc.
Okay, so what might have happened is of late we came to know that in WebEx, basically these are the WebEx links, right, Anup?
Yes, sir.
Our space limit has been exhausted over WebEx. I think Sara has downloaded all the videos and removed from WebEx. What I will do is I will ask him to upload on the Google Classroom and will share the way I'm sharing the videos. Okay, I will do that.
Oh, okay, sir. Thank you.
Okay.
Sir. Hello.
Sir, can we quit? We have another.
Yeah, if you have other classes, please go ahead. If somebody has any other queries or if you're free and want to ask something, you can. Prashant, you are asking something.
Yes, sir, yes. Sir, ultimately these digital signatures are used only for the integrity purpose, not for the confidentiality purpose.
Yes, of course.
Again, for the confidentiality, we need to put up a wrapper like what we do using the RS algorithm for the symmetric key exchange, and then again use that symmetric key on the whole of these two, no, sir. The digital
that's what
signature and
I
the
think.
message.
Yeah, that's what when Rahul was asking, I was mentioning, right? So what you do is see here you are sending the plain text M and the encrypted message digest into the post box. But if you want the confidentiality, what you do is you take the M, comma this encrypted message digest and encrypt using the secret key that is agreed upon between Alice and Bob.
Yes, yes.
So that way you'll also achieve the confidentiality of the data. And but still,
the thing,
yeah, go ahead, please.
no, sir. This what Rahul has said is something like it's correct, I believe, sir. Because on large message, if you apply a hash function, it would be like 224 bits or 256 bit, whatever it may be. But if I want to send a single character, then it will be a kind of overhead to a single character takes only kind of 128 bit, and it would be mapped to a 256 bit or 512 bit value, and again we need to do that. So it would be kind of overhead only, no, sir.
So what you are trying to say here, Prashant, is when the message
is too small.
Message that you are trying to send is too small, you don't want to add the message digest. Rather than that, you wanted to generate the signing on the message as it is. That's what you are trying to say.
Yes, sir.
Yeah, that you are right. But again, I think you have to remember. See, this illustration, whatever that I am trying to say here is in the context of the data integrity alone. But in most of the cases, what people do is also again next class I will talk about how we are going to use the digital signatures in the context of the public key infrastructure to advertise about the public key of the parties who wanted to communicate over the internet. That is the only purpose where you do this hashing, secure hashing, and other thing. But otherwise, in the internet communication, what we do is once you establish a secret key between the sender and receiver, use a secret key for encrypting all the messages, no matter how small or how big. We don't use the way I'm showing it here when you are interested in the confidentiality of the data.
Okay.
So when you use this symmetric key or the secret key will generate you the message, which is the encrypted message, which is typically of the same length as the plain text itself. That way, when you are trying to send only few characters, even the ciphertext also will be of the same length. That way, you are not adding anything extra. Only you are converting it to from one form to other transformation, which is difficult for anybody to understand.
Okay. Yes, sir.
Got it?
Yes, yes.
Okay, so I don't know who else is waiting. Any other
Sir,
queries, Prashant, from your
sir,
side? Or yeah.
can I go?
Anurag, please go ahead, Anurag.
Yeah, sir. One defense against replay attacks I'm thinking of is if we also include the timestamp in the message itself, then can we defend against replay attacks, or is there any other attack still against that?
So you are talking about adding a timestamp to guard against the repeat. Actually, Anurag, yes, timestamp is one way, but one of the most common technique that is used to guard against the replay attack is the counters. So what happens is at the sender and receivers, as soon as they exchange a message, they put a sequence number. You know, right? Sequence number that you use. Each time you send a message, you increase the value for this counter. That way, when somebody is trying to do the replay attack, what happens is you can see that there is a new message which is having the same sequence number as the previous messages, or the new message that you are seeing is having a sequence number that is out of context. So by using this method, you can easily identify whether it is a replay attack or not. Yes, you can use the timestamp, but the using the timestamp is having more overhead than using the sequence numbers. Sequence numbers are anyway used throughout in the internet communication at the different layers in the protocol stack. So we can use the sequence numbers to guard against the replay attacks.
Okay, so we will add the sequence number, append it at the end of the message, and then hash it, sir, or is there any other?
Yes. Yeah, we do that. All that. Yes.
Thank you.
Again, so what I'm talking it is at very generic. And if you look at internet communication at various layers in the protocol stack, all the way from the physical layer to the application layer, there are tons of protocols. They use different cryptographic primitives in different manners to achieve different objectives. And yeah, that way, yeah, there are many different and intelligent ways of using crypto primitives to achieve the secure communication in digital communication systems. Yeah, yet broadly, what I was talking about is correct, but when you go to different protocols, and we have to look at how the standards have defined the way one can use these different primitives, either using timestamps or sequence numbers or message digest or secure algorithms or whatnot to achieve various objectives of secure communication.
Okay, thank you.
Okay, so that way this field is so vast and also quite exciting to learn. So please go through the material that I shared, and hopefully you should do other course that is on cryptology, so that you can go too deep into these principles of cryptography. We'll use in this course these tools more like a black box in the context of secure communication. But I'm not going to talk about, even I don't know what is the math behind these tools. Okay, guys. Any other queries from anybody? Okay, only last 10 students. Okay, Anurag, shall we close in that case?
Yes, sir.
Okay, good. So
Thank
okay, thank you, guys, and yeah, see you on Thursday's class.